The darkness of outer space is not merely devoid of light, it is devoid of the right to make a mistake. We are used to thinking that the path to the stars is paved only with brilliant calculations and steely will. But the history of the exploration of the universe teaches us otherwise. One incorrectly tightened bolt, one micro crack in the heat shield, or an error in programming by several milliseconds can turn billions of dollars and decades of work into radioactive ash drifting in the vacuum. Today, humanity stands on the threshold of the most ambitious mission in the last 50 years. The Artemis program, named after the twin sister of Apollo, is intended not just to return people to the moon, but to create a permanent base there that will become a springboard for a jump to Mars. The National Aeronautics and Space Administration of the United States of America promises us a new era of discovery. However, behind the brilliant rendering images and grand speeches hides a troubling truth. Right where you are watching from, it is interesting to see how far our stories diverge. After the completion of the first uncrewed mission Artemis I, when the Orion spacecraft returned to Earth, engineers discovered something unexpected. The heat shield, which was supposed to protect the capsule from a temperature of 2,800 degrees Celsius during atmospheric entry, behaved differently than computer models predicted. Pieces of protective material charred and broke off differently than during tests. If people had been inside, would they have survived? This question today haunts the leading specialists in Houston. We are at a point where the smallest technical miscalculation can lead to a catastrophe that will forever close the path to deep space for us. If Artemis fails, it will not just postpone flights for 10 years. It could undermine trust in the entire idea of manned astronautics. In the budget of the United States of America, in the geopolitical struggle with China, in the halls of the European Space Agency, everywhere the price of this mistake will be fatal. In this documentary study, we will conduct a full revision of the Artemis program. We will examine the reports of the Inspector General of the National Aeronautics and Space Administration, analyze the construction of the Space Launch System launch vehicle, and look inside the Orion spacecraft. We will hear the opinions of such prominent individuals as Neil deGrasse Tyson and specialists who worked on the James Webb Telescope to understand how close have we come to the limit. What exactly can go wrong? Is modern technology ready to withstand the lethal radiation beyond the protective field of Earth? And why exactly can one small mistake on the way to the moon mean that everything ended even before we had time to start? Welcome to the world of big science, where the price of knowledge is measured in lives and the future of our civilization. To understand why today's mistake can become fatal, we must look back to the time when humanity first broke away from its cradle. The history of moon exploration is not only a chronicle of triumphs, but also a long path of painful disappointments, political intrigues, and scientific pauses that lasted for decades. More than 50 years have passed since the moment Eugene Cernan, the commander of the Apollo 17 mission, left the last footprint of a human boot in the gray lunar dust in December 1972. Since then, the moon has remained lonely. But why? Why did the view of a frozen world, which once united billions of people near television screens, suddenly become uninteresting to those who held the levers of power? To understand this, we need to compare two eras: the era of Apollo and the era of Artemis. Apollo was a child of the Cold War. It was not so much a scientific project as a demonstration of technological superiority over an ideological opponent. When the flag was planted and soil samples were delivered to Earth, political interest began to fade rapidly. The cost of each mission was astronomical. In the peak years, the funding of the National Aeronautics and Space Administration of the United States of America reached almost 4% of the entire federal budget of the country. Today, this figure is less than 0.5%. After the closure of the Apollo program, a period began that historians of astronautics call the time of low Earth orbit. Humanity focused on reusable space shuttles, these shuttles, and the construction of the International Space Station. We learned to live in space, to conduct complex experiments in weightlessness, but we lost the ability to fly further than 400 kilometers from the surface of our planet. Every attempt to return to deep space was broken by changes in political courses. At the beginning of the 2000s, the Constellation program appeared, which aimed to return to the Moon by the year 2020. The Ares 1 and Ares 5 rockets were designed, and the Orion ship was being developed. However, due to huge budget overruns and delays in development, the program was officially canceled in 2010. This was a crushing blow for thousands of engineers. However, it was precisely on the ashes of Constellation that the seeds of what we today call Artemis began to sprout. The fundamental difference between Artemis and Apollo lies in its goal. If Apollo was a short visit, then Artemis is an attempt at colonization. The scientific foundation for this was laid by data from automated interplanetary stations. In particular, data from the Lunar Reconnaissance Orbiter, launched in 2009, changed our understanding of the satellite of Earth. With the help of its instruments, the presence of water ice in craters at the south pole of the Moon, where the Sun never looks, was confirmed. This discovery became a real golden ticket. Ice can be split into oxygen for breathing and hydrogen for rocket fuel. The Moon turned from a barren desert into a potential gas station on the way to Mars. This is exactly why Artemis is so important. It is not just about one more step. It is about economic feasibility and scientific sustainability. However, this is exactly where the main historical paradox hides. We are trying to do much more complex things with a much smaller budget than in the 60s. Historical experience teaches us that space does not forgive compromises. In the 60s, any problem was solved by injecting additional resources. Today, every step of Artemis is under the microscope of auditors and political opponents. In addition, the modern program is not a solo performance by the United States of America. It is a global symphonic orchestra. The Artemis Accords, signed by dozens of countries, created a legal framework for resource exploration. The European Space Agency provides the service module for the Orion ship, without which it will not be able to maneuver in space. The Japan Aerospace Exploration Agency is working on lunar rovers and modules for the station. This makes the program resistant to political changes within one country, but at the same time, it incredibly complicates logistics and technical coordination. Imagine millions of parts manufactured in different corners of the planet according to different standards, which must perfectly dock in airless space 380,000 kilometers from home. History remembers the loss of the Mars Climate Orbiter probe in 1999, only because one group of engineers used the metric system and another used the English system of measures. In Artemis, the scale of such potential mismatches has grown in geometric progression. We look at the Moon not just as a celestial body, but as a mirror of our ambitions. However, history reminds us that every giant leap began with a cautious step. And if in the times of Apollo the mistake was part of a risky game of two superpowers, today a mistake on Artemis can mean the collapse of international trust in the very idea that humanity is capable of being a multiplanetary species. We have waited too long for this return to allow one unaccounted factor to turn our dream into a historical anecdote. When we look at Launchpad 39B at the Kennedy Space Center, we see not just a machine. We see the apotheosis of human engineering thought, embodied in metal, composites, and thousands of kilometers of cables. The Space Launch System Launch Vehicle, more often referred to simply as SLS, is the foundation upon which the entire architecture of returning to the Moon rests. It is the most powerful rocket that has ever successfully reached orbit, and its construction is a complex mixture of time-tested technologies from the shuttle era and completely new systems of the 21st century. The heart of this giant structure is the core stage with a height of 64 meters. It contains two huge tanks, one for liquid hydrogen, another for liquid oxygen. These components are cooled to extremely low temperatures, turning into super powerful fuel. In the lower part of the stage, 4 RS-25 engines are located. These engines are true veterans of space. They were used for decades in the Space Shuttle program, but for Artemis, they have been significantly modernized. Each such engine is capable of creating thrust equivalent to the power of 10 nuclear submarines. But here lies the first technical challenge. These engines were designed for multiple use, but within the framework of the Space Launch System, they become disposable. After each launch, these masterpieces of engineering worth over $100 million apiece simply burn up in the atmosphere or sink in the ocean. Two solid rocket boosters are attached to the sides of the core stage. They are taller than a 15-story building and provide over 75% of all thrust in the first 2 minutes of flight. Unlike the shuttle boosters, these units have 5 segments instead of 4, making them the most powerful solid-fuel engines ever created for human flight. However, their power is accompanied by a huge risk. After ignition, a solid rocket booster cannot be turned off. If something goes wrong, the only salvation for the crew is the launch abort system. But the real star of this technical drama is the Orion spacecraft. It is installed at the very top of the rocket and consists of 2 main parts, the crew module and the service module. The crew module was developed by the Lockheed Martin Company and externally resembles the Apollo capsule, but of a much larger size. Inside, 4 astronauts can comfortably stay for 21 days. Engineers of the National Aeronautics and Space Administration applied advanced navigation systems here based on data obtained from the Hubble Space Telescope. Special star trackers allow Orion to determine its position in space with incredible accuracy, orienting itself by distant constellations. Located below the capsule is the European Service Module, created by the European Space Agency based on the technologies of the ATV cargo ship. This is the engine room of the ship, which provides electricity using 4 solar panels 7 meters long each, regulates temperature, and supplies water and air for the crew. The flawless operation of this module is critically important, as it is its engine that must launch Orion into orbit around the Moon and return it home. However, the technical analysis of the Artemis I mission revealed a serious problem that could become that very one mistake. This is the heat shield. During the return to Earth, Orion enters the atmosphere at a speed of about 11 kilometers per second. This is 32 times faster than the speed of sound. At this moment, the shield, covered with a special material called avcoat, heats up to a temperature of 2,800 degrees Celsius. Avcoat is an ablative material. It is supposed to gradually burn away, taking the heat with it and protecting the astronauts inside. The report of the Inspector General of the National Aeronautics and Space Administration pointed out that during the first flight, the material charred unevenly. Huge pieces of the shield broke off prematurely, creating a risk of local overheating of the hull. In addition, engineers recorded over 100 zones of abnormal erosion. If the entry trajectory were slightly different, or if solar activity increased the density of the upper layers of the atmosphere, this technical nuance could lead to decompression and the death of the crew. Official representatives of the space agency assure that they have a sufficient margin of safety, but scientific publications in the journal Science call for a more thorough study of the aerodynamics of the plasma flow around the ship. Every component of the SLS and Orion undergoes thousands of hours of testing, but the real space is a laboratory where it is impossible to predict everything. The operation of this system is a balancing act on a razor's edge between physical laws and the technical limitations of materials. One failure in the operation of a pressure valve or a micro crack in the composite skin of the service module can stop the mission even before it goes beyond the limits of Earth's orbit. We see how the technologies of the past and the future have collided at one point. A rocket that uses engines from 30 years ago must launch the most modern digital ship into orbit. And in this complex system, every second of flight is a check of millions of lines of software code and the reliability of every bolt. The technical anatomy of Artemis is impressive, but it also reminds us how fragile our presence is in the hostile environment of space. Even the most powerful rocket and the most modern Orion ship have one significant limitation. They are not designed for landing on the surface of the Moon. Orion is only a transport capsule that delivers the crew to lunar orbit and returns them home. For the final jump down to the crater-covered surface, the National Aeronautics and Space Administration of the United States of America made a bet that surprised many conservative experts. The choice fell on the SpaceX company and their ambitious project, the lunar version of the Starship ship. Why did a government agency trust the lives of its astronauts to a private company of Elon Musk? The answer lies in the scales. Traditional landing modules, such as the Eagle of the Apollo 11 mission, were tiny cabins where two people could barely turn around. Starship is a real space skyscraper 50 meters high. It is capable of delivering not two, but dozens of tons of useful cargo to the moon. This changes the very paradigm. We are flying not to leave a flag, but to build a city. However, these colossal scales create technical risks that humanity has never faced before. The main problem is fuel. The Raptor engines installed on Starship run on a pair of liquid methane and liquid oxygen. This is a highly efficient fuel, but it is extremely temperamental. To send such a huge ship to the moon, it needs to be refueled right in space, in low Earth orbit. Imagine, Starship takes off empty, and to fill its tanks for a flight to our satellite, it is necessary to launch from 10 to 20 other tanker ships. Each such launch is a separate complex operation. The technology of refueling in weightlessness is something we still have not done on such scales. Liquid in space does not behave as it does on Earth. It spreads along the walls of the tanks, creating bubbles and abnormal pressure. Any mistake during docking or the transfer of cryogenic fuel can lead to an explosion that will destroy both ships. According to the reports of the Government Accountability Office of the United States of America, it is precisely the complexity of orbital refueling that is the main factor in moving the dates of the landing on the moon. In addition, the question of landing arises. The moon does not have an atmosphere, so Starship cannot use parachutes. It must brake using its engines, descending to the surface vertically. Here, another threat appears: lunar dust. Powerful jets from the Raptor engines can raise clouds of regolith, which will not only blind sensors but can also damage the skin of the ship itself. Scientists from the University of Central Florida, studying the mechanics of particle dispersal in a vacuum, warn the speed of these microscopic stones can be so high that they will turn into a real machine gun fire for any object nearby. Is Starship too big and complex for the first step back? This question becomes the subject of heated discussions in scientific journals. Opponents point out that the architecture of Artemis now critically depends on the success of one private company. If SpaceX cannot work out the technology of pumping methane in space in time, the entire program worth tens of billions of dollars will be at a dead end. We stand before a dilemma. Use old, tested, but limited methods, or take a risk and make a bet on the technology of the future, where one mistake in the software code of the docking system can put a cross on dreams of colonization. Starship is either the key to the universe or the most expensive mistake in the history of astronautics. And every second of testing at the training ground in Boca Chica brings us closer to the answer to this question. If the International Space Station, orbiting only 400 kilometers above our heads, is a cozy shelter under the protective umbrella of the magnetic field of Earth, then the Gateway Station will become the first real outpost of humanity in the open ocean of deep space. This station will not be permanently inhabited. It will serve as a transfer hub, a laboratory, and a rescue raft for crews heading to the surface of the moon. However, its location precisely creates conditions where the boundary between scientific triumph and a fatal mistake becomes thin, like the wall of a pressurized module. One of the most complex aspects of Gateway is its orbit, the so-called near-rectilinear halo orbit. Unlike the usual circular orbits, this route resembles an elongated elliptical ring that balances between the gravity forces of Earth and the Moon. At the closest point, the station will pass only 3,000 kilometers from the lunar pole, and at the most distant point, it will move 70,000 kilometers away. Such complex flight mathematics was chosen not by chance. It allows the station to always remain in the direct line of sight of Earth, ensuring continuous communication, and at the same time requires minimal fuel consumption for maintaining position. However, the smallest failure in the operation of the ion thrust engines, developed by the Maxar Technologies company, can lead to the station going off course and forever getting lost in interplanetary space. However, technical challenges are only part of the equation. The real enemy of Artemis is invisible and merciless. It is cosmic radiation. Beyond the Van Allen radiation belts that protect our planet, astronauts find themselves under a direct hit of galactic cosmic rays and solar energetic particles. According to studies published in the scientific journal Nature, prolonged stay in such an environment without proper protection can cause irreversible changes in the central nervous system, worsen cognitive functions, and critically increase the risk of developing oncological diseases. Official data from the European Space Agency, obtained using detectors on board uncrewed probes, indicate during a powerful solar flare, the level of radiation can become lethal in a matter of hours. This is why the living module of the Gateway Station, which is being created by the efforts of engineers of the United States of America and their partners, will include a special storm shelter zone. In the event of a solar storm, astronauts must immediately move to the center of the station, surrounded by tanks of water and equipment that will serve as an additional shield. One mistake in the early warning system of solar activity, or a delay in the pressurization of compartments, and the crew will receive a dose of radiation that will make it impossible to continue the mission. The scientific journal Science recently published a report analyzing the impact of lunar dust on human health inside enclosed spaces. Even if the station is in orbit, microscopic particles of regolith brought on spacesuits from the surface can become a serious problem. These particles have sharp edges because they were not subject to erosion by wind or water, and when they enter the lungs, they act like crushed glass. On the Gateway Station, the air purification system must work with flawless efficiency. If the filters fail, every breath of the astronaut will bring them closer to chronic lung damage. We must understand, at a distance of 380,000 kilometers from Earth, help will not come in a few hours. If on the International Space Station the crew can get into a rescue capsule and be home in 3 hours, then the path from Gateway to Earth will last at least 5 days. This makes any critical mistake in the oxygen regeneration system or water purification potentially a death sentence. Every bolt, every sensor, and every line of software code on board this lunar outpost is the fruit of the efforts of thousands of people who know. In deep space, survival is not a right, but a result of every second of struggle with the hostile environment of the universe. When we speak about one mistake, we do not mean just a random coincidence of circumstances. In astronautics, a catastrophe is usually the final link in a chain of small oversights that merge into one deadly stream. For the Artemis program, this chain can begin at the most critical moment, during the transition from circumlunar orbit to the direct descent to the surface. These are those same 7 minutes of terror that are well known to researchers of Mars, but in the conditions of the Moon, they have their specific, cold cruelty. The first scenario of a critical mistake is related to the communication system and autonomous navigation. Unlike low Earth orbit, where a network of satellites ensures almost instantaneous data transmission, on the Moon we depend on the deep space network of the National Aeronautics and Space Administration. During the descent of the Starship lunar module to the South Pole, where the terrain is cut by deep craters and high mountains, a risk of falling into a radio shadow zone arises. If at this critical moment a failure occurs in the software of the landscape recognition system, the crew will find themselves in a situation where they do not see the surface and do not have communication with Houston. Imagine, a ship with a mass of hundreds of tons descends on jet streams in the complete darkness of a polar crater. If the sensors erroneously identify a shadow from a rock as a flat area, we will get a repetition of the tragedy that Apollo 11 barely avoided, but with much more severe consequences due to the dimensions of the modern ship. Official reports of engineers indicate that even a small error in the LiDAR algorithms can lead to a landing at an angle exceeding the allowable 10 degrees. A Starship overturned on its side on the Moon is not just a breakdown. It is the immediate isolation of the crew without any possibility of takeoff. The second scenario is the quiet expansion of lunar dust, or regolith. Scientific studies published in the journal Science describe regolith as one of the most aggressive materials in the solar system. Due to the lack of wind erosion, every particle of lunar dust is sharp as a shard of glass and has a static charge. During the operation of engines during landing, a colossal cloud of this abrasive rises. One small mistake in the sealing of the docking unit or external hatches, and the dust begins to destroy the seals. History knows examples. During the Apollo missions, astronauts complained that dust corroded the layers of spacesuits and disabled zippers. In the conditions of a long-term Artemis mission, If regolith enters the air circulation system of the living module, it will destroy the filters and cause a chemical burn of the lungs of the astronauts in a matter of days. This is a slow catastrophe, where a mistake in the protocol for cleaning spacesuits leads to a systemic failure of all life support. The third scenario is the human factor in combination with the psychology of deep isolation. We often forget that the Artemis crew will be at a distance of 384,000 kilometers from Earth. If during the Apollo 13 mission the explosion of an oxygen tank became a challenge for the intelligence of engineers, then today the complexity of systems has grown thousands of times. The psychological pressure from understanding that the path home will last at least 5 days can trigger cognitive overload. One mistake in the interpretation of telemetry indicators during a critical situation, and an astronaut can make a decision that, instead of salvation, will block the safety system. According to the reports of the Inspector General of the Space Agency, the modern automation of Orion and Starship is so deep that the crew may lose manual control skills in extreme conditions. If the main computer fails due to the influence of solar radiation and people cannot immediately take the initiative, the mission will end in seconds. We have seen how this works in aviation, but in space there is no possibility to carry out an emergency landing at the nearest airfield. Each of these scenarios emphasizes the main point. In Artemis, there are no insignificant details. We are building an incredibly complex pyramid where every brick is the work of thousands of specialists. However, it is enough to have one crack in the foundation, one unaccounted physical process, or 1 second of delay for this entire construction to collapse, burying under it the ambitions of humanity for a whole generation. We analyze these risks not to frighten, but to understand the true price of our desire to become a space species. In the 21st century, space has stopped being a space for romantic dreams. It has turned into an arena of tough geopolitical struggle where flags on lunar regolith weigh more than any diplomatic notes. The Artemis program is not only a scientific project of the National Aeronautics and Space Administration of the United States of America, it is a fundamental tool of soft power. And that is exactly why the price of one mistake here goes far beyond a technical failure, threatening to change the balance of power on Earth itself. Today, we are witnessing the beginning of a new space race, where the main rival is not the Soviet Union, but the People's Republic of China. Beijing is actively developing its own program for exploring the moon, planning the landing of taikonauts and the construction of the International Lunar Research Station in cooperation with the Russian Federation and other partners. If the Artemis mission suffers a catastrophic failure, it will create a strategic vacuum that China is ready to fill immediately. Losing leadership on the moon will mean losing the right to dictate the rules of the game in managing space resources, which is the basis of the Artemis Accords. These accords, signed by dozens of countries including Japan, Canada, and the states of the European Union, establish the principles of peaceful use of resources such as water ice. However, as experts note in analytical reports for the Congress of the United States of America, the legitimacy of these rules rests on technological leadership. If the American Space Launch System rocket or the Orion ship demonstrates its unreliability, international partners may begin to review their alliances, looking for more stable technological allies. The economic consequences of a mistake will be no less destructive. The Artemis program has already cost American taxpayers tens of billions of dollars. The report of the Government Accountability Office of the United States of America has repeatedly pointed out budget overruns and delays. In the event of a large accident, especially with human casualties, political support for the program could evaporate instantly. We have already seen this in history. After the crash of the Shuttle Challenger in 1986 and Columbia in 2003, spaceflight stopped for years, and funding was subjected to sharp cuts. However, today, the situation is more complex. The failure of Artemis could lead to a space winter, a period when the governments of democratic countries generally abandon the idea of manned flights to deep space, considering them too expensive and dangerous. This will mean stopping the development of technologies that have critical importance for the future, from new energy systems to methods of mining minerals beyond our planet. Scientific journals such as Nature warn that stopping the program will throw humanity back 50 years, making us again hostages of one planet. In addition, there is an ethical and psychological aspect. For the generation that grew up on videos from Mars rovers and images from the James Webb Telescope, Artemis is a symbol of progress. The failure of the mission can sow disbelief in science as such. If the most well-funded and technologically advanced nation in the world cannot return to the moon, it will put in question the very ability of humanity to solve global challenges. The geopolitics of the moon is a zero-sum game. Every meter of territory at the South Pole, every drop of water in the craters of eternal shadow becomes a subject of controversy. A mistake on Artemis is not just a lost ship, it is a lost opportunity for Western civilization to establish standards of democratic and open space exploration. We risk leaving the moon under the control of regimes that have completely different views on the freedom of scientific research and the distribution of resources. Therefore, when engineers at the Kennedy Space Center check every sensor, they hold on their shoulders not only the fate of 4 astronauts, but also the future of international law and the world order. The next chapter of our history on the moon will be written by the one who turns out to be the most resilient to mistakes, because in this race, second place may mean complete oblivion. We have come to the final boundary of our research. Having analyzed thousands of pages of technical reports, looked at the complex mechanisms of the Space Launch System launch vehicle, and sorted out geopolitical intrigues, we again return to the same question. Is this path worth such a colossal risk? If one mistake on Artemis indeed can put a point in the history of our expansion, would it not be better to stay on Earth, focusing on solving earthly problems? The answer to this question lies not in the plane of mathematics or budgets, but in the very nature of our civilization. Famous astrophysicists, among whom is Neil deGrasse Tyson, often emphasize that space is not just a place where we fly, it is a mirror in which we learn about ourselves. Space today has ceased to be just a cold stone in the sky. For scientists, it has become the 7th continent of Earth. This is a chronicle of the solar system where in every layer of regolith the history of 4 billion years is captured, which it is impossible to read anywhere else. If Artemis succeeds, we will get not just a base at the South Pole. We will get a technological revolution. History has taught us that every penny invested in space returns to Earth 100-fold in the form of new medical technologies, energy-saving systems, and methods of water purification. However, if that same fatal mistake happens, we will lose not only money and iron. We risk losing faith in the fact that humanity is capable of great achievements. We must accept the fact that space will never become safe. It will always be an environment where every breath is provided by a complex machine, and every second of life requires the flawless operation of software code. But this complexity is exactly what makes us humans. The philosophy of expansion is based on the idea that stopping is degradation. If our ancestors were afraid of one mistake during the crossing of oceans or the conquest of the poles, we would still be limited to one patch of land. Today, we stand on the threshold of a new era. The Artemis program is our exam for maturity as a space species. It is a challenge to our intelligence, our will, and our ability for international cooperation. We see how government agencies, such as the National Aeronautics and Space Administration of the United States of America, work side by side with private companies, creating an incredible symphony of progress. And even if one mistake stops this process for some time, it will not be able to kill the desire for knowledge. We conclude our analysis on a note of cautious optimism. Space is a cruel teacher, but its lessons are priceless. One mistake on Artemis may mean the end of the program, but it will not mean the end of humanity. We will learn from the debris, we will analyze data from the James Webb Telescope, and we will build rockets again, because our path lies through thorns to the stars. And what do you think? Are the risks of the Artemis program justified in the conditions of modern crises on Earth? Are we not rushing too much, trusting the lives of people to automated systems and private corporations? Do you believe that exactly your generation will see the first permanent settlement on the moon? Or will this dream again be postponed for the next 50 years? Share your thoughts in the comments, because the future of space is the business not only of scientists, but of each of us. Like and subscribe to the channel. Become part of our crew. In this cold space, we hold together until the last atom dissolves into nothingness. Thank you for walking this deep scientific path together with us. Remember, even in the darkest corner of the universe, the light of the human mind is capable of paving the way forward. See you on new orbits.